Very good afternoon to all of you. I request Professor Chaudhuri to kindly switch on his microphone and his video. Yeah, thank you, sir. So I welcome all the attendees in the post-lunch session of this online summer school on advances in signal processing and machine learning. Just to apprise Professor Chaudhuri, in the morning we had the two talks by Professor Surendra Prasad and by Tapan Gandhi, and which was well attended by over 300 to 350. The attendees were there all throughout the day itself, and there were a lot of questions, and because of which the sessions usually got delayed by about 10 to 15 minutes. So before I request Professor Chaudhuri to deliver his talk, as a customary, I'll introduce him. He is the director of IIT Bombay and also the Kamalnayan Bajaj Chair Professor in the Department of Electrical Engineering in the same institute. He works in the area of image processing, computer vision, machine learning, and computational haptics. Some of the areas where he has contributed significantly include depth recovery from defocused images, image super resolution, blind deconvolution, hyper-spectral image visualization, and pattern recognition in remote sensing images. In the area of haptics, his major contribution lies in haptic rendering of point cloud data, kinesthetic perception, and haptic data communication. Professor Chaudhuri has received numerous awards for his research. These include the G.D. Birla Award for Scientific Research, NASI-Reliance Industries Platinum Jubilee Award for Application-Oriented Innovation, J.C. Bose National Fellowship, Professor H.H. Mathur Excellence in Research Award of IIT Bombay, Shanti Swarup Bhatnagar Prize in Engineering Sciences, Swarnajayanti Fellowship, and Hariom Prerit Dr. Vikram Sarabhai Research Award. He is also a distinguished alumnus of IIT Kharagpur and has been a fellow of the Indian National Academy of Engineering, Indian Academy of Sciences, National Academy of Sciences, and Indian National Science Academy. He is also a fellow of IEEE and has been on the editorial board of IEEE Transactions on Pattern Analysis and Machine Intelligence during 2006 to 2008, SIAM Journal of SIIMS since 2018, and International Journal of Computer Vision since 2004. He has also been a visiting professor at several international universities. With these words, I welcome Professor Chaudhuri, and I request him to kindly share his screen.
Hold on.
Yeah, sir. So
it should come now.
Yeah, it's coming up.
Yeah. So shall I go ahead now?
Yes, sir. Yes, sir.
Okay, so thank you everybody for joining this afternoon. I think you had a very short lunch break, but since most of you are at home, I think you could get a good supply. But I know that after lunch, it will be difficult to keep you awake. So that's the problem. Okay. So I have to make this talk a little bit more interesting so you don't fall asleep. But let me tell you, since most of you come from a very varied background, from starting from early days of college to maybe the late college. So I'm going to talk on a topic which is probably now a very hot topic by going by the name machine learning. And you already, this particular this summer course that you are, webinar series that you are attending is also titled as a part of that is a machine learning. So I'm going to talk about machine learning because this is one of the first day of lectures. So many of you are not very familiar with the machine learning aspects, what it is, and there may be a lot of this brouhaha going on all over, saying that, it can solve all your problems, it's like a panacea, okay, all your problems. So I made my title as a machine learning, a technology for all, because we wanted to show you that you don't have to be a computer scientist or an electrical engineer or somebody else, mathematics person to do machine learning, anybody with a simple, let's say, class 12 kind of mathematics background should be able to do machine learning with the currently whatever we have at home, or maybe, you know, certain codes that are available at different places. So let me first give you a very simple background of, yes, you know, how it evolved. So maybe it's always good to know, because I assume most of you are student of science. Okay, if not, you know, absolutely. So right, we will not use too many equations or anything. So you are also, those who are not belonging to the sciences stream, you are also, I think you can have some basic idea of what is machine learning. So if you look at the evolution of science as a stream of learning, it started, you know, very early with human civilization. And right now it is actually said that there are 4 different paradigms, okay, for science. The first one, okay, is of empirical evidence. What it means is that you observe something, okay, and see that, oh, this is an evidence. Like morning, early morning, if you see in the, you know, little winter time, there would be, you know, water droplets on the grass or something on the tree leaves. So that means there must be some condensation happening. There must be something. So you try to deduce what has gone through. Or let's say, for example, one of the most common thing would be, like we say that, you know, that Aristotle's saying that buoyancy, you know, when you do said that eureka moment. So there is something called buoyancy. So people know, see, even before that, people know that even something a little heavy or something else, certain things can float in water. Like we, you know, since early life of human beings, people have been using ships, boats, and others, right? We see, you know, birds flying, so that means flying is possible. But then you have to put it in a scientific framework and decide on that. So the first one is on the empirical evidence. Okay, so for example, if you look at it, so Galileo and other before Copernicus, if you look at, go back to them, say they just observed various phenomena and try to, you know, prescribe what's possibly going on. Then later on, I think around, you know, say, I would say, um, after about 1,000 years or so, then as slowly the scientific theory started getting developed. So you develop a theory, okay? You have so many laws of physics, so many other things that happens, okay? So people started developing the theory. So that actually solidified the entire process, whether it's mathematical or it's a physical or it's a chemistry. So it's theory. Then what happens around 1940s and 50s onwards, then when the computer came in, then people realized that I, you know, can simulate a lot of things, and through that I can learn a lot of science out of that. Okay, how does certain thing behavior under certain circumstances, which is otherwise not possible. So the computational science became a paradigm. That's a third paradigm. And over there, you have some kind of a model. And based on that, you try to justify whether this model is good or not good. Then comes to the current one, which is the fourth paradigm, which is a data science. So here, the data is the supreme. So what you do is that you say, I don't care what is the underlying process, what's going on. Why do I recognize a cat as a cat? Okay, that's really important. As long as I am able to recognize a cat. So if that's the kind of idea, so you feed in a lot of such kind of data, like people observe certain things in all this data, and let a system learn that what it is, you know, what is going on, like whether, so I'll come to that a little bit more in details, and that's what is the data science. So there's a fourth paradigm, and this is where actually all these machine learning, they actually belong to. So there is a large number of parameters, you know, which is inside, so you don't even know how to interpret them. There are a lot of other things, but at the end of it, you have some way of interpreting, or rather coming out with a decision process. Right? Okay, so I'll talk more about that at a later stage, but let me go to the next page. So this is the foundation, you know, one single way of explaining what machine learning today is, that you have certain input data which is given to you. Okay, so data comes in, and you have certain observations. So observations is on the output side. So you observe something. The problem could be of generally two types that we normally face in life. One is called the regression. Regression means you have a data set coming and you want to predict what would be the next one, or what would be after tomorrow, what would be the stock market value tomorrow. These are something, whether it will be raining tomorrow. So that's like a regression. And the other one is a classification. Something or certain kind of thing, and you want to say what it is. Does it classify to class 1 or class 2? Whether what you see, whether it's a cat or it's a rat or something else. So that's a classification problem, right? So these are the two things. So you have, a lot of such kind of a training data. If I see it here, my answer is yes, it's a cat. If I see this one, it's a dog. So what happened is that my decision process, whatever it is, if I put it in this black box, so that's actually the thing which is learning. So this learning, I'm calling it like an F, which is nothing but a mapping function. Those who are in science, you know what is a mapping function. So what it does, it maps the input data here to something to either like classified, whether it's a cat or a dog, or you say what would be the possible value of how many COVID patients would be tomorrow. So you do the regression. So the common thing is that almost any mapping F can be learned today with the kind of expertise that many people have done, they got it today. Is that so almost, with a fairly good kind of confidence, we claim that a good number of mapping functions can be learned. And better the learning, of course, better the performance. So if you learn, how to recognize, let's say, a special kind of bird, so many of them, and you can actually classify them. So that's what is, your better would be your accuracy. Now, so how does it learn? So I gave you a black box model. So you have what we call is a training data. Later on will be something called testing, for which I do not know the output. Let's say this training data, and I know what is the classification for that. And then what you do, this mapping function is parameterized in terms of large number of weights. The parameters theta, we call it here. So this is actually called the weights, right? So this one, and how do you learn? So you decide something called a loss function, L theta. So when you do it, it predicts something. And if it is different from this classification here, so there is an error. So that's the loss. So there, you can actually define a loss function. And once you have this loss, then the more the loss, that means you're away from a good classifier. So you try to do some differentiate this one, and then you keep moving in a direction so that the loss is minimized. And if you're able to do that, then what you can show is that the loss gets minimized every time you show a lot of different types of these examples and their accuracy, whatever the actual class level, and then you learn. Once learning is done, loss is minimized, okay, you learn the corresponding mapping function F. So what is important here is that today, given the current status in the machine learning community, a large number of type of possible loss function L can be minimized. See, those of you who are in mathematics and say, okay, I give you a loss function and I said somewhere that I have to take a derivative. And I know there are many functions I can actually cook up, okay, where derivative doesn't exist. Then how do we do it? So there are different kinds of techniques that people have developed. So some of you may know how to do it, or you can learn. And this kind of things would allow you to reduce the loss. So the choice of loss function is important because that tells you that how is that loss function relevant to this input data, to the training that you are providing in terms of the classification of the regression testing. Okay. And second thing is that I have put something here as a theta. Theta is the network. Okay, it's a network architecture. It's some of the network weights and others. I'll show you an example. And this network is also very important. If it is a small number of parameters, which is very few, so it's like a normal machine learning. But if theta is very large, you have large number of such weights and others, then we call it like a deep learning. It's very, very deep. Okay, so example on how it looks. So a typical architecture of the network may look like this. So you can have, say you have, so here we're showing you certain number of input layers. So let's say you have 4 of them and you have n number of such examples you are giving. So each one goes to the next layer. This is the hidden layer 1. This would be hidden layer 2. And you can have n number of hidden layers, large number of hidden layers. Okay. And you take a weighted sum of the output of this one. So those weights are the theta that I talked about. Okay. So this is W1, W2. So they would be all weights there. Okay. So they could be fully connected. They did not be fully connected. It's up to you. Okay. And at the end of this one here, like when you see the end of a layer, so we try to bring in certain non-linearity, some kind of a non-linearity function that we add. And then after that, we put it to the next layer. And this keeps on going, you know, you can have it. And at the end of it, you will have an output layer. And this output layer will tell you whether this should fire or this should fire. It could be, here it could mean like I have 3 possible classes. One could be like a cat, and the next one could be rat, and the third one could be bat. So these are the 3 classes. So only one of them should fire, not all 3 of them. Okay. So that's classified. That's how we define. That is called one hot. Okay. Now, if in this particular case, it's a very shallow network, but when we actually go for a large number of them, there's not a lot of such things one after another, then your theta, you know, the dimension of theta is very large. So you have to learn a large number of such parameters. So that's actually an issue that what we have to handle. If network becomes deeper and you can learn a lot of things, that's what a lot of difficult, I think, mapping function you may be able to learn. So let me go to the next one. So what do we make out from this? I told you that we add some layer called the nonlinearity. So when you add the nonlinearity layer, okay, this actually helps. So this is sometimes called an activation function, and this helps in limitations of linear method. Now, what do I mean? Normally, you know, traditional pattern recognition literature, if you read some of it, so most of the classifier that we talk about, they are linear classifier. So I separate them with a line, okay, like or plane in multiple higher dimension or a hyperplane. I separate them. Now, that is easy to understand. It's good to define it, and if you can, very good. But it has a lot of difficulty. For example, one thing I can tell you, that supposing I have a simple 2-bit case, and we define an operation called XOR. So most of you, those who know about Boolean algebra, you know what is an XOR. So there, actually you have, depending on the value of 2 bits A and B, 0 or 1, you can have 2 sub. Your mapping would be based on 1 in 2 cases, and the other 2 cases is 0. And you can mathematically prove that no matter what linear method you use, you cannot classify them separately. You single classifier will not work. But if you use nonlinearity, so you are not restricted to selecting your boundary as a line. So you can actually do something like this, and you may be able to classify even XOR. Okay, so this is a very simple example. That's beauty, but of course, at the same time, you realize we understand the linear functions so well, okay, compared to the nonlinear. So sometimes that's a difficulty because we do not know the behavior of the function, particularly when theta is very large. Second thing, which is, if you see, it's an interesting thing, is the number of unknowns that you have, because number of unknowns means number of thetas that you have, weights, is a lot more than number of equation. Number of equation means each training sample will give you, let's say, 1 equation, okay, for loss. So usually your number of training samples is much less than the number of the weights, because it's a very deep learning, particularly deeper the network, then that happens. Then the question is that how do I actually find out so many of them? And this is nonlinear equations, it's very difficult, but that's actually helps. Even though if you do, so they, you know from the third aspect that we talk about here, that if you have a nonlinearity, then any functional minimization or optimization that you do, then there is no guarantee that you go to the global minima. Okay, so it will get stuck into a local minima, right? So you just try to do it, you take a differentiation and see when it becomes 0. So then it goes to the nearest one, and that's a local minima. But turns for machine learning, most of this multiple, you can have a large number of multiple this local minima, but they're good enough, most of them, for the job that you are doing. They are quite close to the actual, you may never know what is the global minima, but you can get close to that. Okay. Now, let's look at the next one. So what I said so far are the good things you use. What are the difficulties? So number one, when you have a big network, your training may take too long. It's training. Sometimes there are network which learns for days and days and days. Okay, so it takes very long to learn. Okay, of course, actually when you do the testing, it doesn't take that much time. It's much faster, but it's actually the training, because I have to do the entire manifold. I have to travel while learning the loss function that that we are talking about. Other thing that happens, that when you have some type of training data, I may actually end up doing overfitting or underfitting. Okay, so in that particular case, so my actual, I may overlearn something and I'm not able to generalize. So when I show them something different, some different pictures, it will not be able to recognize. Your performance degrades drastically when if you have done overfitting for your data. Okay, then the choice of loss function is important. So the question is that how do I know which is the best loss function? So that's a problem that we have to handle, right? And since there are too many weights, what we do sometimes is that this creates a problem, because it's an under constraint problem. So we some additional constraints, like we put the weights should not be very large, things like this. So some constraint on the weights also we add, so that we can get a reasonably good, acceptable accuracy. Okay, so solution is what we want. Now, based on that function I told you, that f of theta and how it is learned, there are various types of learning. Okay, one is a supervised learning. That's the most common. I show some examples. So I give some training data, and there is for each data, input data, I have an output. I show them in pairs, and the system learns. So this is the simplest possible and the most used thing. It's called supervised learning, right? So this is the key thing. But then in some cases, I may not have too many examples. Okay, I may have enough number of examples for explaining how does a cat look like, how does a dog look like, because they're everywhere. But supposing I tell you to train something like a leopard. Okay, now of course I know in IIT Bombay we have leopards. Okay, but how often do I get to see it? I don't know how many times I take the picture. Okay, so those training for few cases would be very few examples. So there is a technique by which you can say that, okay, I learn predominantly from where when you have a large number of good data, then you do something called meta learning and try to transfer it to help when you have a smaller number of inputs, training data. Zero sort is another one. Zero sort means I train you for one set of kind of let's say some classifying problem, but then I try to use it for a completely different type of thing. Let's say I have never seen a leopard, but I have seen cats, I have seen rats and other things, so many other things. And maybe from there, I have some idea that how it is supposed to look like. I may have some kind of a textual description of a leopard. So by having that, I can actually figure out that, oh, this is a leopard. So that's called a zero shot. That means I have seen something, I have been trained on something which I have seen, but I'm taking a decision on something which I have not seen before. Okay, so that's called zero shot learning. Then there is something called reinforcement learning, where we don't have like this kind of supervised learning where you can give you input and output pairs. But what we have instead, that some kind of a reward and punishment scheme. So like, for example, if you are doing well in your school and others, how do you know? Because at the end of the semester or year, you get, and that's like a reward or a punishment. If you have not done well, you fail. Okay. So you get an intermittent way some feedback. And this is also something is, kind of a learning is possible. It's called reinforcement learning. And of course, one of the most, I think everybody wants something, but which is difficult, is completely unsupervised learning. So here is no training data available and you want to learn something. Okay. There are certain, like you might have, I'll show you one example, which is an unsupervised learning over there, where I don't need a specific training data. So it's basically data manipulation that you do. But in general, everybody tries to go for unsupervised learning because getting this training data is very, very difficult and time consuming. In certain cases, you can get them, certain cases it's very difficult. So everybody would like to ideally have unsupervised. I am not, isn't it wonderful? I don't train you for anything. And I tell you, oh, write some code in Python or something. So it's like that. But yes, there is a way people try to do it. And you will see some examples. Now come to the, for most of you would be wondering, should I learn machine learning or not? Because everybody talks about machine learning. I think before COVID came in, very few people talk, so those days there was no topic of COVID. So the only topic, the maximum, I would say hottest word was machine learning. Nowadays, COVID has replaced that. But the machine learning, why is this craze? Okay. You have to understand the reason for that. See, most often, it actually offers much better results than the classical methods that we are all comfortable with. Okay. So it gives you, finally, I want good results. Everybody wants good things. Right? So if it's good, let's use it. That's the spirit. Second thing, which is very, it's an indirect one, but it's very useful, that most people, who work on this area, they make their codes and data, training data and others are publicly available. So if you search like GitHub and others, many other places or someone's web page, you will see these are given. And many of them you can just download and run on your system. They are so good. Okay. So that has popularized it. So I don't have to really know what's going on. And that's one good point. This community has done a favor to all of us. So that's why it can be used as a plug and play system. Just like anything, if I have to assemble, you have to run, you have to debug, you have to write code, then of course you wouldn't do it. But I can simply try it on a new data set and say, okay, how it works. So that's what is happening now. Okay. Similarly, some interfaces that have been designed, Python and others, are very simple. See, most of you who are, know how to do coding, for you it becomes like very easy. I've seen students pick up so quickly, okay, this kind of things because of ease of things, as well as there are a lot of this, search engines where you say, oh, how to write this one, and it's all available. This help. And lastly, no specific user expertise is required. So today, if I tell you that, classically something like a matched filter, you have to know, you need to be an expert on that. You need to know what is a matched filter. Here, I don't need to know anything. You simply said, look, here are some pictures of cat, here are some pictures of dog. Can you tell me, can you ask a computer to find out which one is a cat, which one is a dog? That's it. Okay, you define your problem like this, and the system learns. So that's what is actually happening. So what I'll do is that I'll show you some examples, of these applications of this, and I'll go through it a little quickly. Okay, and then if you have any questions, so I can take it. And I'll take it mostly from the image processing domain because that's what most of my life I've spent on. Okay, so first of all, it's like I'll show you something which is comes under unsupervised learning. Here it is a 1-bit image capture. It's an extremely low image acquisition machine where you can just say that measure, your typically your picture is around 8-bit or 12-bit, right, depth. But I want to take it with 1 bit so that I want to compress and no computation, nothing else. So you can do it in onboard, like in places like when you have drones and others where power is a problem, bandwidth is a problem, so that I want to compress it. So typically your engine looks like this. So you have your data that is coming in here, and you just take some maybe 8 of them, 8 such frames, and collapse it into a single one, okay, by doing some random weightage. So it's absolutely random numbers you generate, you compress, and now for 8 such frames become 1 frame. This 8 becomes another one. Then what you do, each one, you can actually do like a dithered quantization. So basically, it just everything is quantized to 0 and 1. So you have lost the details, right? It's a 0 and 1. Then what you do, because now I can, so this is every point is a 1 bit. So I can take 8 of them and merge into a single one, which will be 8-bit system. So that's like 1 packed frame, right? So that means I have 8 into so many of 8, 64 of them I've packed into 1 of them, right? Now, then I give it like this. So my basic mathematics would be, when I data, I combine all this process into some matrix operation as phi, and just take the sign value 0 and 1 or -1 + 1, whatever you call it. Is up. So this is my forward process. What would be, so I captured the picture like this. So it's extremely fast, nothing is required. But then I lose my information. So what do I do? My job at the receiver would be that given y, I would like to find, because that's my actually all this video volume. So that's what I have to do. Now it seems that I can actually train a network which looks like this. So this is an EU net, and it learns on its own by showing a lot of examples, because I can actually generate any image volume you do, I can take it. So somebody doesn't have to give me, because if I have the image, I generate this as my the compressed data, and I have final output. So there is nothing like I need to get a separate kind of a training data and train it. Okay. So I'll not go into how it is trained. Okay. But basic idea is similar to what we did before. And I'll show you an example. This is the original one. Okay. This is like some of the typical things that you are using for other methods, but using the proposed thing, you see that I could get a lot better. Of course, there are some losses, like you see that this is not so good here because you have drastically compressed the data, but that's what the purpose is. Okay. Similarly, if you look at here, this is the raw image. Okay. If you see here, and if you see, this is basically the video. This is the standard, like your if you use your HEVC, one of the best kind of a compression engine will do it like this. Okay. And whereas here, this is what you do. So you'll see it is very, very fast and extremely compact data. And if you see that, next one, yes. So if you look at the computation time wise, so we save a lot of, like in a factor of 5 or 6, we gain. And the quality also, they are at the same quality. So this is where they are. And so that means there is some gain we have, which was not available. I give you now another example. Here, it's a video-based person re-identification. So what does it mean? So you have, let's say, along the boundary of some building or some secured place, there are something, and then you have cameras at different places, and people are moving around. So you want to know if somebody has walked here, when he is going here or something, so that I don't want to know whether this is X, but I know that whether this same person X has gone to this location. So it's identifying the same person rather than identifying an individuality. Like individuality means that I know that this is Sham X. Okay. No, I'm not looking at the identification, just the same person. Okay. So for example, here you see that they are in completely different looks. So how do you say this and this are the same? These two are the same, completely different look. Similarly here, you see that other two. So that's the job. That's So you have a gallery which gets put into from here, and this is the query. Okay, and you want to find out which one they match. So actually, this you can take it from signal processing background. So you have this video data that you have, you use each one of them as a CNN. And normally there is something called RNN data, which is a very standard. So which is, I'll come to that later. But we said, okay, instead of that, we can, so this is how you combine the past data with the present data as an output level. So it's a, like those who know like autoregressive process, it's like more like an autoregressive process. So we said like you can also use a moving average part. So that's the MA part of it. So I'll show you this one here. This is a typical RNN, how it looks like. Your output is fed back here with some weight, and this is how you get. In our case, your input is also added with some weights as well as the output. So this is the moving average part, and this is the autoregressive part. So this is the new model that we are saying. And if you, and these two are identical ones. One is query, one other is the gallery. And this kind of thing is called sometimes the Siamese, because they are identical network, just like Siamese twins. Okay. And you take the difference, they should give, if they match well, I should get a good score that matching. They are not the same. So I'll show an example. If you give like this as a video, and then this is the first time it says this is matching with this data. Similarly, if you give this, it is matching with this. So look at this, your environment, background, everything is different. Another thing I'll tell you is that activity detection. So supposing people are doing something and some of them are normal, like some of them are abnormal. I mean, if you're in a classroom and if you're jumping, then it's abnormal. So abnormal, there is no definition what is abnormal. You know, it depends on the context. And in a classroom, anything other than listening, studying, you know, listening to the professors or, you know, writing notes, okay, watching something, these are normal. Anything else would be abnormal. So if I show you like this, so before that, so we needed to first do the tracking, that what is the important thing in my scene, in the video. So I'll show you an example where we show that is a complicated object, the basketball here, it is being tracked so that we know that it is, you know, I can actually track. Here, this person in green, the basketball, see, somebody is covering, somebody occluding, all of them, but we are still able to actually do this, you know, see, continuing like this. So you are actually able to track them. So this is a tracking problem. See, it's going on like this somewhere, but we are still latched on to this gentleman over there. Okay, I'll show you another one here. Here you see that this is the person is being tracked. Okay, so he's only little bit of the person is being seen, but you're still able to do it. Here is another one. Person we are actually tracking. So some blocking is there, somebody moves, so it's gone there. Now, once you do this tracking, then the question, you want to find out what are they doing, what are the activities. Like say here. So now, see each one below that, we have something written that is walking, waiting, others, and they have a different color code. So when you have 2 or 3 people having the same color next to each other, that means they are put into the same group. So right now they are all into the same group. Now they are walking, so all of them you could see that, right? Similarly, this is another group, the people who are coming to you. So walking, so this is another person, they are not correlated, they are completely different. Now, of course, somebody is cycling, the system doesn't know how fast is this. So this is also another example to show that there is a, you know, something called time scale. So it thinks that it's moving. Okay, so it's a walking, some of them would be, you know, so all kinds of things are doing, right? Look at this, there are several groups, they're all being recognized like this. Okay, then, so this is the network. How does the network look like? It's complicated, but it's some form of LSTM networks, those of you know. So that's what it works on at different scale. Now, using that, now we say, okay, what is the normal, you know, somebody's normal behavior is that if you walk, so this blue is the one, okay, is a predicted trajectory, and the red one is the input. So if the predicted and the input are matching, that means it is doing what it is supposed to do. If it is different, then of course you would shout, oh, this is something abnormal. So look at this. This is looks like this is walking on the road. They are turning, all of them. So I go to a case where they are not the same now. Okay. So let's see here. And here I'll write here the corresponding. So now look at this person. He throws something. So this is, of course, abnormal, right? So here also you will see that on the right hand side, the predicted and others. So it detects that there is a mismatch between what is predicted and there is the actual. So then it will complain that this is not the same. Is that okay? Now, I give you another example. Now, this is like a really like a deep network, okay, deep learning. So here, I give you like here's around 6 images, okay. Now, out and then tell you what is it that the corresponding person, whoever the photographer who put all this together, what is he looking at it? What is it? So we are looking at finding co-occurring objects in a set of crowdsourced images. So here, of course, we would say that this is actually the tiger is what the person is interested in. And here, of course, one of them, this is an outlier. This is something is different, okay, a bear, okay. Question is, so the image co-segmentation is that given this set of images, whatever is common, you segment them out, okay, from there. So that means I would like to segment them out here and not this one, of course, because this is different. I am not recognizing that this is a tiger. I'm just recognizing that I'm doing the common segmentation. So here is one work to show you like co-segment, it's called co-segmentation network. So here, if you see here, what you do is that you are doing 2 at a time. So here you give one image, here you give another one. So this is an encoder set, this is an encoder decoder network, and you are learning this, the mask, which is to be segmented. So for this is the mask. So this is the, some cases the training would be given, and some cases towards the end, it will automatically generate that mask. Is this okay? Now, when you give these 2, it will also detect this as the mask. And this is the training. So there is a basically how you train the weights by giving the, some examples and whether they belong to the same class or not. So this is a common thing that actually they learn. And similarly, if you give one with this one, you know that this is not matching. So this system, there is a decision network here. You will see it here. That will say, oh, it's not same, so I'll not learn. So it will stop learning. You are giving a wrong information. So it has that kind of intelligence into the system. And then I'll show you an example like this. So if I give you this picture here and here, it generates the corresponding co-segmentation map. Of course, I'll just show you here some errors, but because this is just probably the shadow or something, or maybe some other patch of, on the runway. If you give it here and see it here, oh, this is like another method, and this is the proposed method, okay? So here you see that this and this kind of extra patches has reduced, okay? So this is, you are able to get only the plane. And even though look at this, they look differently, the colors are different, okay? Even this is different. So it's not looking at a specific shape. Now here we had shown them enough examples, but I told you that there is something called few shot. Like I don't have too many examples, but I still want to do it. So this is an example where we take a set of data and we feed it. See, this is called a guide set. So this is just we put them a guide, and then we give a set of images here. And actually here in this case, we can actually, instead of 2 at a time, we can give any number of them, 8, 10 images at one time we can do it. And then we do some kind of your learning. So let's not go into that learning process, but I'll show you an example here. Now we give you this data set here and see what you get. From here you get the horse. Okay, so here also horses are there. Similarly, this horse is there, but this is outlier. It has not detected. Similarly, the flight, you see that here it is, this is not detected. This is not detected. Similarly here, if you look at, so these are actually the guide set, last one. So we have given the guide set. So similarly here, if you see, this is the guide set. these dogs, they have been well segmented. In most cases, this is the cat. The cat classes have been well segmented. And see that the toughest thing would be if you have a black and white, they are completely two different part of the spectrum, but they are able to find out, that this is what is going on. So that's the power of machine learning. So in order to give you some time to ask questions or to clarify doubt, before that I would say that to conclude, we demonstrated the usefulness of the machine learning technology, see how it can be done, simple things. Normally, in earlier days, we used to do something called encrypted features. So that means what is a feature to be classified? Here, what happened, let the machine come out with that. The CNN and others that you might have heard, actually, they find out the relevant feature. This brings to something what is known called end-to-end training. That means your features are also part of your training. Okay, so everything is trained. But there are problems. So failure points are not known. I give you something and I do not know what time it will fail. Whereas in the classical area, sometimes you can predict quite well that when it is likely to fail. So that's why you see that occasionally you read like Google comes out with completely ridiculous answers sometimes because it failed. It was like a drastic failure. Performance guarantee is not assured. I cannot tell you that this will work with a 95% accuracy. It works for that data, I can do that, but finally I have to show it with somebody outside. What would be the performance? Some failures are catastrophic, as I said. Sometimes it could be absolutely arbitrary results you may get because somewhere you don't know what it has learned. That's our problem. And next is that what about explanation? See, supposing you tell me, I tell you that this is a dog, I recognize. And then if you ask me, why did you say it was a dog? I can actually answer that question. But this machine cannot. Actually, that leads to some new kind of area, which is called the explainable AI. So they try to also find out on what basis I am giving you that kind of, the decision. And then the recent emphasis also on the, as I explained earlier, is an unsupervised learning. And there is another one is that typically this learning and others, it needs a lot of hardware. You might have heard like GPU and other usage, okay, because it's become computationally very demanding. But finally, I need this on my mobile phone and some of them even smaller things, some maybe in your microwave oven, maybe somewhere else. So this has to be an embedded or edge ML. So this is, the computing has to be done with a very, very low resource, okay. So that's also, people have been working on that. So I would stop at this point saying just only one take-home point to ponder for all of you, okay, is that, see, if you remember, we started with a black box, okay, with F inside. And now after that, when we do it, we said my black box has learned, okay, that how to do this classification or regression. So that's why I said my machine has learned. But the question I ask you now, did you learn? Did you learn means what? How the machine did it. Okay. So machine has learned because I have given him enough training data sets. So it has learned the mapping. But I have no idea what is this mapping. Okay. Because I am not able to quantify this mapping in my own language. So if the machine may be good, it is maybe intelligent in our, but that intelligence has nothing to do with my intelligence because I have never learned a lesson other than I build, only thing is that I built that machine. Okay, I wrote the code. Okay, I developed the system, but I don't know, like, how it works. So that's something that you should wonder, and that would actually take you to the explainability also. So thank you, and if there are questions, I can take it.
Thank you. Thank you very much, sir. There are a few questions. I'll take up one by one. First one is by Kapil. Is there any relation in between the number of data and number of hidden layers?
So how many hidden layers can you have? So basically, there are also earlier some works that if you in place of increasing number of hidden layers, if I increase in vertically, the same layer may have too many weights. So sometimes there is an equivalence can be established. So it's not just the number of, I would not say only the number of hidden layers, but it's also the total number of weights. So if you have too many weights and too few of training data, naturally it's a highly under constrained exam, the case of learning. So what you do is that you will learn, it will not try to learn properly. Okay, so you will do underfitting, and so it may have very poor results when you put it into the testing. Is that okay? So that would be my answer. So you have to be rational. There has to be some good number of number of freedom in terms of the weights has to be learned, has to somehow be comparable with the number of training data. Is this okay?
Okay, sir. The second one is by Dharmendra Mahato. Is there any way to deal with small data set to achieve good model performance? And what are the hardware requirements for deep learning model training testing purpose?
So first is that, as I said, that you have fewer training data. So in that case, if you do it purely on the few data set, then it will not work. So you have to do using something called meta learning, where you try it with something else, some other big data. Okay, and there you learn something, and then you try to fine tune it with some kind of this smaller data sets. Okay, so that is the idea. Coming back to the second question, that what would be the hardware? So normally, as of now, you need GPU. Okay, most cases that you need certain kind of graphical processing units to speed it up. Otherwise, learning would be very slow. If you are using a small few, size network, maybe yes. Okay, but when you go for really a large network, where all these learning intricacies, whether the network is learning, whether the weights are converging, all those things, that you will be able to do it if you have some access to GPU. Is that okay? But there are services available in clouds and others when they actually allow, okay, so people to use that.
Okay, thank you, sir. The next one is by Bharti Katyar. Can you please give example on k-mean clustering and k-nearest neighbor algorithms, and what will be the difference between the two?
K-means and
K-mean clustering and k-nearest neighbor algorithms.
Okay, so see, these are, I tell you what, so when you actually take, see, this is called clustering technique. So clustering technique means somewhere your data is clustered around different points, okay? And those who come from actually, they can say that these are nothing but mode analysis of the distributions. So where the clusters are nothing but the modes of the distribution. You want to detect, mode detector, which is actually, for in higher dimension, it's actually a difficult problem. As long as the dimensionality goes up, it becomes difficult, okay? Now, when you do this k-means classifier, or the clustering, so you take a point over there in one of them and find out how many of the k of them, how many of them are the nearest neighbor. So you get tag to that particular, that they belong to the same cluster, and you keep on iterating over there, okay? So similarly, if you k nearest neighbor, if you do it, so there is a similarity over there, that when you define the loss function, so because there also you are trying to minimize something by putting it like this, by looking at, but the problem would be that in some cases, these are computationally, there is no guarantee that it will converge to the center. So this is a problem of the mode detection. So I would recommend you that first you take up a book on statistics, that how how comfortable one is in detecting mode. In images and others in 2-dimension, many of them use something called half transform. Okay, I don't know whether you have heard the term half, H-O-U-G-H. You can look it up. That's one efficient way of doing it, but it can be done when the parameter space is very low. Otherwise, there would be a problem. Okay, next question.
Yeah, so next one is by Chetan. Is NLP a supervised or unsupervised learning?
No, NLP is something to do it in the textual and others, right? It's a language. So there, the two things are opposite thing. I mean, I wouldn't say opposite, basically independent. Okay, you can have training, okay, in your NLP also, when you do something where it could be unsupervised. In certain cases, this could be supervised. See, for example, you might have heard like word to wake or something, where this is nothing specific to that, but you go through a book or something, you just find out the contextual relationship with one word with its neighbor, and that is encoded in a vector space, which is word to vec. Okay. On the other hand, when you want to do something like understanding, language understanding, okay, then actually you have to, have certain model of the language also required sometimes. That is also part of that. So some grammar, syntax would also come in. Then similarly, there is a bigram, diagram, all those things would come in. So I would not, so that would be, so there certain things can be learned from the way it is given, and certain things have to be done supervised. Yes.
I'll take up the next one. That's by Parnika. Could you please tell me that can we use unsupervised learning algorithms for spectrum sensing for 5G networks?
Oh, so I think that would have been the perfect person, would have been Professor Surendra Prasad this morning. Okay, he would have been the expert.
Okay.
Right. So
Okay,
the spectral sensing, see what happens is that spectral sensing, if you try to do it in 5G and others, the issue is not, my understanding is not one signal, because there is a lot of crosstalk, because this is a multi-access channel. So there are a lot of people who would be doing it. So there would be certain kind of traditional, let's say, bomb welch learning and others could have been used. But I think now in 5G, because the timing restriction is very narrow, because it's a 5 millisecond system. So I am not sure what is the right thing to, so I may not be the right person to answer what is the right algorithm to do that. Okay, because your time, remember, it has to be very, very fast. Your latency, system latency is 5 milliseconds. So can you get a response within that? I think that's where it will take you down.
Okay. So there are last three questions. The one is by Sangeeta Yadav. Image co-segmentation can be used for object detection also, and how to decide how many inputs we should provide for accurate learning.
For object detection?
Yes.
Yes, of course. Actually, there is a, see, if you look at your camera, most of your mobile camera, when you look at your selfie or other, you're taking picture, if someone's face is there, it gives you a bounding box, right? Something like a box, many cameras. So what is it doing? It's actually face detector. So it's like an object detector. Okay. So this earlier, there used to be a classical method called Birla and Jones method, which most of these people were using. They were doing good, but they were not machine learning based. Now what happens is that they try to do it on a machine learning based. So it comes with certain kind of attention mechanism. So find out when you try to get something, which part of the image is trying to give you an attention. So there is a feedback that tries to find out and try to basically accentuate those set of points which are actually responsible for recognizing. So those are the detected set of points. So then you do the bounding box based on that. So that's what, as of now, most of the technique use that particular philosophy. Okay.
Okay. So second last question is by Ravi Kiran. Can we use data augmentation to reduce the biases?
Reduce the bias.
Yes.
So
Bias.
see, that data augmentation is a technique to show that more, examples, but more than that, actually, there are two things. Okay, you have to see why we do data segmentation. One is that noise sensitivity. Okay, in certain cases, we add a little bit of noise and give it back to them, and then we try to find out what is the solution to that. So this is typically your when you encoder kind of thing. So that's where many of them they use that. Okay, so you show examples which is a little perturbed from the previous one. Another class of reason for doing it is giving you, see, a classical reason. I mean, when you talk about pattern recognition, we ask for few things which is very important in classically. One is rotation, translation, and scale invariance. Okay, can actually see somebody as a let's say a bicycle. If it is rotated, is it still a bicycle? If it is still bicycle? And if you like taking a picture instead of close picture, if you take it very far up, is it still recognized as this? So that's a scale. So those are the cases you have to understand. So in order to, most machine learning techniques that we talk about, anything that none of them are this, RST invariant. Okay. So in order to bring in little bit of invariance, because you do not know the object is really aligned, so you do little bit of movement, rotate others, create this, and you add that one so that you create invariance. So that's another reason. So it's not about the bias. The bias, it's still the same data. It's a cat, but it's a rotated cat partly. Okay. So it will not, in my opinion, remove much of bias, but it will give, basically it's an invariance is what is being looked at. Is that okay? I hope you're happy with that.
So I'll take up the last question. It is by Ashutosh Mishra. Is there some efficient way to run ML models over low-cost microcontrollers?
It depends. Okay. The microcontroller, it depends, like, supposing,
I'll
see,
take up
this is
the
what I
second
said,
part
the
of
edge.
his. Sorry, sir.
Yes.
I'll take up the second part of this question. Maybe that will be much more clearer. He said that I have tried one taking the binary of trained models and putting it directly in a FIFO memory, then accessing it in the AVR microcontroller. Is there a more efficient way to do so?
What is that? It depends on what you want to learn. See, the learning is not auto, this thing, because finally you take the output, but see, normally the way we discussed is actually you are taking a decision based on that. So whether, see, you should not give the stream data unless it's a, you should take it to control, do so, it should be the control unit for the microcontroller, right? So what would be the control signal that you will get? That gets derived from certain sensors, whether temperature or others, and take that one, process it, and then it has to be a very minimal thing, because your decision would be whether to increase, decrease, and all. If you do it, I'm sure your controller would be able to handle, because earlier days there is neuro fuzzy controller for washing machines. These are also only doing something similar to that. So if you expect little bit, yes. If you want to do too much, you pack into that, I'm sure that it will not be able to do that. Okay, I hope this you're happy with that.
Thank you. Thank you very much, sir. Within 1 hour duration, you have completed the talk, as well as you have answered nearly all possible questions which have been there. And
thank you.
Thank you very much, sir, for sparing your valuable time. And especially during this pandemic, I know you have been very much busy during your administrative work also.
Okay. Good luck to all the participants. Bye.
Sure. Thank you. Thank you very much, sir. Okay. Bye-bye. I request all the attendees to kindly fill up the feedback form link that has been shared in the chat section. The feedback form link will remain open for next 20 minutes, and thereafter we will close it. Tomorrow morning, kindly join us for the second day at 10 a.m. Kindly join between 9:45 to 10 a.m. itself. Thank you very much. You can leave the meeting after filling up the feedback form.